So today we're going to be talking about binary analysis. We're going to be talking about malware analysis. We're going to be talking about reverse engineering and vulnerability research, and how we can automate all three of those using machine learning, scripting, other bits and pieces. So breaking it down to a few main areas. First of all, we're going to cover why automate in the first place. Then we're going to cover some use cases, people who would benefit from that sort of automation. We're going to cover quick wins, so tools that you could use right now to help you with binary analysis automation. And then finally, we're going to cover some general high-level techniques if you're interested in writing your own automation, or if you're brand new to scripting, places to kind of generally start. First things first though, who actually am I? Well, my name is James Stevenson. I've been working in the computer security industry for around about 7 years now. Worked in areas from security operations to software engineering to penetration testing. And these days I lead a team of vulnerability researchers, kind of the intersection of machine learning and vulnerability research. Now today I'm here as an individual, not here as part of my organization, not here as part of my university who I do a PhD in, just here as a person talking about some cool tools, some cool research. So let's jump straight into it, right? Why automate in the first place? There's a quote I pulled offline. There are many like it. Generally, what this quote is saying is it's saying automation is about replacing tasks. It's not about replacing people. So when I talk about automation, we're talking about automating out the boring stuff, right? We're talking about saying, how can we give people cool tools, cool techniques to help them do what they're doing? If we take a hypothetical and we say that you all work in a technical role that really doesn't have much automation, we could probably say that 80% of the time you're doing the monotonous, the boring, the kind of tuning the crank kind of work. And 20% of the time you're doing the interesting, the novel work. And with automation, what we want to do is flip that, right? We want to say that 20% of the time you're doing the boring work, and 80% of the time you're doing the interesting, human touch required work. And so today, when we talk about automation, that's what we're talking about. We're talking about automating out the boring stuff. We're talking about giving people tools to help them do their jobs. And we're not talking about replacing people with AI intrinsically. So we're going to talk about three main types of users and talk about how they will benefit and can benefit from binary analysis automation. We're going to talk about malware analysts who will look at malware, want to identify malware. We'll talk about reverse engineers who are looking at understanding complex systems. And then finally, we'll talk about vulnerability researchers who are interested in identifying and understanding new versions of vulnerabilities, or maybe old versions as well. We're also going to talk about three main questions that all three of these users have. And then when we talk about quick wins, we'll talk about how we can answer those questions using automation. The first question we have is, how similar is one binary to another? The second question we have is, what does this code in front of me actually do? And then the third question we have is, where is this given component, or where is component X in the thing that I'm looking at? And what we're going to do next is we're going to dive into these questions and have a look at the specific kind of sub-questions for each of those three types of users, and then tools that we could use right now to help us answer those questions. So, first question. How similar is one binary to another? It's kind of a binary diffing question, right? As a malware analyst, maybe we've got an older version of a piece of malware and a newer version of a piece of malware. We want to figure out what's changed. As a reverse engineer, maybe we've got the same question, right? We've looked at an older version of a binary. We want to figure out what's different in the newer version. And then as a vulnerability researcher, maybe we've identified a vulnerability in an old version of a binary, and we want to see if that vulnerability is present in a newer version of it. So a quick win, a tool that we could use right now to help us solve this, and there's actually a good handful right at the bottom there as well, but we're going to talk about a really simple tool called just another differ. As the name may suggest, it's just another differ. Primarily, what just another differ will allow us to do is it will allow us to look at two different binaries, and it will allow us to say, well, function A in binary 1 looks the same as function B in binary 2. And function B in binary 1 looks the same as function C in binary 2, and so on. The way that works is we take our two binaries, we decompile them using Ghidra, we then iterate through all of the functions in binary 1, compare them to all the functions in binary 2. We then use fuzzy string comparison to take the decompiled pseudo C code and look at which of those functions in those two binaries look the most similar. We do that selection, and we create this kind of mapping file. Again, that mapping file saying, function A, binary 1, looks the same as function B in binary 2. Now, this top name I mispronounce every single time I talk about it. So we're going to call it fuzzy string matching, because intrinsically, that's what it is. And again, the way that works is that takes our decompiled C code, and it looks at the minimum level of character edits needed to go from one function to another. And then that allows us to do that comparison, to say, well, this function is close enough to this other function that it's probably the same thing. Let's run through a quick example. We're going to take two binaries, we're going to run them through just another differ, we're going to have a look at the mapping file, and have a look at what's been produced. We're going to take BusyBox. We're going to take a stripped version of BusyBox and an unstripped version of BusyBox. Stripped meaning that we don't have function names, variable names, stuff like that. We run that through just another differ. We can see all that decompilation happening there using Ghidra headless. And then finally, right at the bottom, we're doing that iterating over all those functions. That produces this mapping file. This is the HTML version. This is the text version. We focus on one of those. Here we can say that just another differ has said that the function in binary 1, add fname, it has a 70% correlation with the function fun_00653e. And that 70% confidence is saying that these two functions generally look the same at kind of a 70% ratio. And we can confirm that, right? We can just open Ghidra and we can have a look at those two functions. So here we have the stripped version. On that side, we have the unstripped version. And as a human being, we can say, yeah, generally those look about the same. There are some differences, and that could be due to kind of a whole range of things. It could be due to Ghidra having a bad day. It could be due to the compilation, the decompilation. They're slightly different versions maybe, but generally, those are probably the same thing. And so there we have it, right? We've answered our first question. That's not even using machine learning, that's just using a bunch of scripts. We've answered that question of, are these two binaries the same? Or what's different between them? So let's jump to that next question. What does this code in front of me do? I'm looking at a binary. What's it actually doing? As a malware analyst, maybe I've reversed a bunch of malicious code and I'm looking at some new code and I want to see if it has any of the similar traits of code I've looked at before. If I'm a reverse engineer, maybe I'm reversing a really complex state machine, and I want to, just at a high level, understand what it's doing. As a vulnerability researcher, maybe I have a back catalog of functions that I know to be vulnerable, and I'm looking at some new code, and I want to say, are any of those vulnerabilities present in this new bit of code? So the quick tool that we're going to use to do that, the quick win that we could do right now, is a tool called Tweezer. The idea behind Tweezer is the first part, it allows you to generate we're going to call it a database. It's not a database, but a database of vectors of known functions. And then when we have a new target, we vectorize all of their functions and compare them to that database, allowing us to understand what this function we're looking at is like. The way that works, we have that top phase of kind of aggregating all of those vectors. So we grab all the binaries that we're interested in. Ideally, kind of unstripped binaries. This could be your malware samples. This could be your vulnerable code samples. This could just be a bunch of unstripped, interesting Linux binaries. Again, we decompile them using Ghidra. You might be able to tell I quite like Ghidra. We then run a word-to-vec model against all of the functions in that binary, all the kind of decompiled C code. And that produces this vector file that we're going to basically pickle and use later on. So now we have a new target binary, one that we don't really know much information on, but we're interested in learning more about it. We do the same. We decompile it, we vectorize it, and then we compare the functions, the vectors of those functions, against our stored vectors. The idea being, the hypothesis being, that where we have similar functions that are close to each other on that vector space, they're probably doing the same thing. So for this, we're using a word-to-vec model to translate those strings, those C functions, to vectors. And then we're using something called cosine similarity to understand the difference, the distance between those functions. So let's imagine that as this kind of table. This is our pickle file, or this is our vector space. Every time we get a new binary to add to kind of our knowledge base, we vectorize the functions and we place them on that vector space. We get a new binary, we place it on the vector space. We get a new binary, we place those functions on the vector space. And then when we get our new target binary, the one that we're interested in learning more about, we also place that on the vector space. But this time we can say, well, what's this function close to, right? what is nearby? And in this case, we can say the red function that we don't know anything about is closest to this green function up here. And so we can hypothesize that if green is some sort of file IO function, red might be some file IO as well. So let's run through a quick demo. So we're going to generate our vector pickle file here. For this, we're using kind of a generic Talos dataset. Now we are creating, or at least matching, using BusyBox. We're saying take BusyBox, vectorize all of the functions in BusyBox, and then compare that to our vector space. And then we produce this mapping file, very similar to the previous mapping file. Here we have all of the functions in BusyBox, and on the other side we have all the functions that they are closest to in that vector space. So right at the top here we have function underscore 001, etc. And Tweezer has said that the function that is closest to in the vector space is this function called whirlpool update. So again, we can probably hypothesize that this function right at the top might have something to do with updating in one way or another. Last question that we're going to talk about today. Where is this given component, right? So as a malware analyst, maybe I'm interested in identifying packers or cryptors or command and control systems in a binary. As a reverse engineer, maybe I'm interested in finding authentication or entry points to a binary. And as a vulnerability researcher, I'm probably interested in identifying vulnerabilities in that binary. The quick win, the tool that we're going to talk about now to allow us to answer this question, is a tool called Monocle. Monocle allows us to perform natural language search against a binary. So we can say, hey, take this binary and take this find criteria of command and control systems, of entry points, vulnerabilities, and go find them in that binary, all in kind of natural language search. The way this works is we provide the binary, we provide that find criteria, it goes off, it decompiles it. It then iterates through all of those functions and provides that function along with that find criteria into a large language model. That large language model then goes and produces a score between 0 and 10 for how much that function meets that find criteria, along with an explanation on why. That then feeds into this kind of a live analysis. At a super high level, I'm not going to dive into how LLMs work or how this specific LLM works. One of the main things I want to get across today is that we can start approaching these problems, we can start approaching these techniques with off-the-shelf tools and off-the-shelf techniques. So this is using Mistral, which is an off-the-shelf large language model. This sort of stuff would obviously be better if we use tuned and kind of specific models for this problem space, but it's a good step in the right direction. So let's run through a quick example. We are going to provide Monocle with the pure auth-d Linux binary, and we're going to give it the find criteria of memory corruption vulnerabilities. Really simple. It then goes off and begins its analysis. We can see a bunch of functions down here, entry and a few kind of obfuscated ones, where it's giving them a score of 0. It said no memory corruption here. There's one in the middle, it's given it a score of 1. And it said, well, no memory corruption happening here. But, if some of this code was to change, there's a potential. And right at the top, it's given one of these a score of 10. And we'll focus on some of these areas. And it said, well, yep, there's direct writing to memory here. There's iterating over it multiple times. And there's no bounds or checks or validation happening at all. Okay, awesome, right? That sounds like potential memory corruption. So this is the Ghidra output, and I appreciate the contrast is horrid. But generally, we can validate that, right? Let's take that function that was given a 10, let's open it in Ghidra, let's figure out if we agree or not. And we can confirm, right? No bounds checking, there is a loop, it is writing to memory. So potential memory corruption. Now, obviously, we're missing a lot of information here, right? The LLM doesn't have information like what are these actual memory spaces related to? Is there any bounds checking happening before this function is called? It doesn't know. Neither do we from just looking at this function. But it's a step in the right direction, right? As a researcher, we can use that as a first port of call to go, okay, maybe this is something we want to look at. Again, going back to that original point of being an additional tool in our tool belt to kind of help us point us in the right direction. So those are all the tools I wanted to talk about today. The last thing I wanted to talk about is if you're here, maybe this is your first B-sides and you're new to scripting, you're new to automation, generally what direction should you go and how should you kind of pick this up? There's three broad areas that I like to follow when I build tools, when I script, when I do things like this. So I like to have an idea, and that's generally who's going to use this tool and why are they going to use it, or how are they going to use it. I like to have a goal, so that is kind of setting a time frame. How long do I have to do this, and what am I actually creating? And then finally having inspiration, right? So what is the goal of this? Why am I doing it? So we're going to run through one more tool and talk about how it hits these three criteria, and then we'll go from there. So the last tool we're talking about is a tool for generating seed corpus files for fuzzing using machine learning. For this, we had an idea, right? The idea was that we wanted to accelerate fuzzing, especially that kind of onboarding phase of fuzzing. The goal was I basically had a day off work, and I said, well, I have 4 hours, let's figure out how to do this. And I wanted to make a really simple command line tool. The inspiration was that I was using LLMs with Monocle, and I said, well, I really want to use an LLM when it comes to fuzzing. So that's where AutoCorpus was made. The idea behind AutoCorpus is it allows us to generate seed corpus files for fuzzing. At a super high level, when it comes to fuzzing, we mutate off a seed corpus set. So we need a representative data set to start fuzzing. And what AutoCorpus allows us to do is it allows us to generate that corpus set without having to make it ourselves or pull it from online or anything like that. The way that works is we can provide it with an existing corpus dataset, which we then take a sample of and feed to the LLM, or we can just provide it with a prompt and say, hey, I want config files, maybe I want some JSON files that have this information in. All of that then gets fed into the LLM, and it produces this seed corpus input file, or files. So let's run through our last example. For this, we're going to be creating some awk command config files for a fuzzing run against BusyBox again. For this, we provide the tool with two inputs. We provide it with a single corpus file. This is kind of a generic awk command file that you can find online. And we provide it with the criteria of generate some awk command config files. It then goes off, it does its thing, and after a while, it comes back and it's generated a handful of input files for your fuzzing run. Right at the top, we can see an example of these fuzzing files that it's created. Similar, but different enough to that original file that we provided it. And then on the far side here, we can see that it is indeed a valid awk command config file, which is really important when it comes to fuzzing. So there we have it, right? We had an idea, we had a goal, and we had inspiration. So that is the talk coming to an end. The last thing I wanted to talk about, myself and a good friend Nathan are running some training, creating some resources in the binary analysis and machine learning space. If anyone's interested in getting some free resources or learning more about what we're doing there, jump to this website, drop your email address in, and we'll let you know kind of as and when resources come live. However, once again, thanks all for coming along. Thanks to the organizers and the volunteers for having me here today. If you have any questions, feel free to ask me now. Come find me later. I'm on LinkedIn. I'm on GitHub. And yeah, cheers everyone. Any questions?
You were using Mistral 7B, which is a general purpose model, right?
Yeah.
So, and as of a week ago, we have Mistral for coding, and before that we had Falcon with Code Wizard, etc. Do you think they're going to perform better for this specific task, or general purpose ones might be actually, or task framing might be better?
Yeah, so the question is around the choice of large language models in this case. You know, if you go on Hugging Face, there's 101 different models for 101 different purposes. I think generally what I'd recommend is just trialing a bunch out. I haven't done that. I've used some code models. They didn't really do what I wanted. But in my case, I found, you know, generic models did the job enough where I felt confident demoing it. But they still don't do the job well enough where I think you could use this in a real VR or other environment. I think intrinsically, it comes down to finding a really good model and then fine-tuning it. Building an adapter or something like that is what it will come down to in kind of a real enterprise environment. Great. Right at the back.
You said at the start you had like a bit of an objective of swapping the 80 and 20. So for the tasks with the tools that you mentioned, do you feel that you've achieved that goal? Do you think that they're close? How do you think they do in terms of swapping that 80 and 20?
Sure. So the question generally is going back to that original slide where we had this kind of 80-20 split, kind of 80% of the time doing this monotonous, doing the crank kind of work, 20% of the time doing the interesting human touch work. And the question is, do the tools we covered today help us kind of bridge that gap, I suppose? And I mean, if I'm honest, these are tools I have made in my afternoons and days off. In practice, they are not going to solve world hunger. They're not going to solve world peace. But I do think they help demonstrate what we can do with this sort of technology if we adopt it and apply it to these new problem spaces. And so I think not even years down the road, we'll have tools like this that significantly help us get that direction. Great. No questions right here? Yeah. Yeah, so the question is, in all the tools I covered, we used Ghidra headless, and the question is, have I noticed Ghidra being better than others? In practice, I'm lazy, and I know how to use Ghidra headless, and so I have used Ghidra headless. I've seen really good results with Ridare, especially Ridare's intermediary language. That looks really promising. But in practice, the quick answer is because I'm lazy and I like Ghidra. But I've seen really good results with Ridare, and also Binary Ninja is also a really nice tool, and I've seen really good results with that as well. Yeah. Yeah. Yep. So the question is, especially feeding into the large language model and, well, into Tweezer as well, why did we use the decompiled kind of pseudo-C over the disassembly or over intermediary language or something like that? In practice, especially for the large language model, my gut feeling, because we were using generic models, was that they're a bit more like human language, and so they'd be a bit better at understanding it. Especially because we're including all the symbols. So let's say we have a memory corruption vulnerability and it's a mem copy and it has a certain field. All of that information is there. While if we were looking at some data marshaled disassembly, maybe we wouldn't have that information. Great.
Okay, thanks, James.
Yeah, great. Cheers, everyone.